All right, let's talk about carboxylic acids. They're everywhere, in your salad dressing, your painkillers, even the nylon in your clothes. They are, without a doubt, one of the most important building blocks in all of chemistry. But for a chemist, the real question isn't just what is it, it's how do I make it from scratch? Well, today, we're going to crack that exact code. Let's dive in.
So here's our game plan. First, we'll zero in on our target. Then I'm going to lay out the master map for you, a whole strategic overview built on 3 core pillars: oxidation, hydrolysis, and a really clever trick called carbon chain extension. And finally, we'll turn all that theory into a practical playbook that you can actually use.
So what exactly is our target? Well, at the heart of every single carboxylic acid is this specific little structure right here, the carboxyl group. Just think of it as a single carbon atom that's double bonded to one oxygen and single bonded to another. This one little arrangement is the powerhouse behind the sour taste of vinegar, the magic of aspirin, and the strength of nylon. It is a true VIP in the world of molecules for sure. Now look, there are dozens, maybe hundreds of ways to whip up a carboxylic acid. But here's the secret. Almost every single one of them boils down to just 3 fundamental strategies. These are the 3 pillars of carboxylic acid synthesis, and together they form our master map. And here it is, the master map itself. So pillar 1 is oxidation. Think of this as upgrading a carbon you already have by giving it more connections to oxygen. Pillar 2 is hydrolysis. This is kind of like using a water key to unlock a more complex molecule and reveal the carboxylic acid that was hiding inside. And then there's pillar 3, carbon chain extension. This one's a real game changer. This is how you actually make your molecule longer by sticking on a brand new carbon. Let's kick things off with pillar 1, oxidation. The basic idea here is pretty simple. You take a molecule that's almost there, something like a primary alcohol or an aldehyde, and you just upgrade it. You force its carbon atom to form more bonds with oxygen, and in doing so, you transform it into the carboxylic acid you're after. This first strategy is beautifully direct. If your starting material is a primary alcohol, and you can spot that by looking for the CH2OH group, you can use a strong oxidizing agent to go straight to your target. That R you see, that just represents the rest of the molecule, which hangs out and stays intact. And if you start one step closer with an aldehyde, the job's even easier. That reagent spotlight on the slide shows you the heavy hitters for this job, chemicals like potassium permanganate or Jones reagent. These are the real workhorses for this kind of transformation. Okay, oxidation can also pull off a pretty wild trick with molecules called alkyl benzenes. Basically, it's a benzene ring with a carbon chain just hanging off of it. But this is where things get really dramatic. A powerful oxidizer like hot potassium permanganate doesn't just tweak the chain, it demolishes it. It cleaves the entire thing right off, leaving just a single carboxyl group. I mean, look at this. Whether you start with a 1-carbon chain or a 4-carbon chain, you get the exact same product. But, and this is a big but, here's the crucial constraint you have to watch out for. If the carbon attached to the ring has no hydrogens to grab onto, the reaction fails completely. It is an all-or-nothing deal. All right, on to our second pillar, hydrolysis. The name pretty much tells you the strategy, right? Hydro means water, and lysis means to split. So here, we're using water as a chemical tool, often with a little help from an acid or a base, to break apart other molecular groups and reveal the carboxylic acid we're looking for. A classic example of this involves a group called a nitrile, which has that cool carbon-nitrogen triple bond. As you can see on the slide, this reaction happens in 2 really clean steps. First, water turns the nitrile into an amide. Then, if you keep the reaction going, that amide hydrolyzes again into our final carboxylic acid. And this shows a key element of chemical control, which is highlighted in the process note. If you use gentler conditions, you can actually stop the reaction halfway and just isolate the amide. It's like having an off-ramp on the chemical highway. Now, other groups are even more eager to react with water. Acyl halides and anhydrides, we call these activated derivatives, which just means they are totally primed and ready for hydrolysis. An acyl halide will react with plain old water, but if you add a base, it happens even faster. Anhydrides are just as simple. 1 molecule of water splits them cleanly into 2 carboxylic acid molecules. These are incredibly reliable reactions to have in your chemist's toolkit. Hydrolyzing an ester is another key technique. But here, the conditions you choose really, really matter. If you use an acid as a catalyst, boom, you get the carboxylic acid directly. But if you use a base, like sodium hydroxide, the immediate product isn't the acid, it's its salt, which we call a carboxylate. To get to the final carboxylic acid, you have to add an extra acidification step at the very end. That's a super important distinction when you're planning out a synthesis. And that brings us to our third and final pillar, carbon chain extension. Now this one is really special. With oxidation and hydrolysis, we were just modifying a carbon skeleton that was already there. With this strategy, we're doing something much more powerful. We're actually making the skeleton longer. The undisputed star of the strategy is the Grignard reagent. You take this reagent, you react it with carbon dioxide, usually in the form of dry ice, and you forge a brand new carbon-carbon bond. A little acid workup at the end, and there's your carboxylic acid. The key insight here is that you produce a molecule that is exactly one carbon atom longer than what you started with. Chemists call this ascending the series, and let me tell you, it is an incredibly powerful tool for building bigger, more complex molecules. Okay, so we've got our three pillars. We've got our strategy. Now let's put it all together and see how these tools actually work in practice. This is where the theory becomes a real-world playbook. So here is pillar 1 in action. On the left, we're taking an alcohol, butan-1-ol, and we use a strong oxidizer, the Jones reagent, to get butanic acid. On the right, we start a bit closer with the aldehyde, butanol. It's already halfway there, right? So we only need a milder reagent to get to the same finish line. It's a perfect example of choosing the right tool for the job. You've got two different starting points, two different reagents, but the exact same product. Now this slide shows two different master strokes for adding a carbon atom. Pathway A is the nitrile route. Notice how it combines two of our pillars. We first add a nitrile group, and then we use hydrolysis, that's pillar 2, to convert it to the acid. Then pathway B showcases the power of the Grignard reagent from pillar 3. We form the reagent, react it with CO2, and we're done. Two completely different pathways, but they both achieve the same critical goal, making the carbon chain longer. And you should never, ever underestimate the sheer force of oxidation. This isn't just for simple tweaks. Look at the top example. A powerful oxidizing agent chews off both side chains from this ring, creating two carboxylic acid groups. And on the bottom, it gets even more dramatic. The reaction literally breaks open a ring, unspooling it into a linear molecule. This just shows how robust and powerful this strategy can be when you need it. Phew, okay, we have covered a ton of ground. But this slide right here, this is your ultimate takeaway. This is the strategic playbook, all on one page. Seriously, think of it as your mission planner. You just find your starting material in that first column, let's say it's an alkyl benzene, boom, the table tells you your strategy is vigorous oxidation, and it even reminds you of that critical detail. The whole chain gets lopped off. Or maybe your mission is to add a carbon atom, just find the Grignard reagent row, and there's your plan. This is your cheat sheet for mastering carboxylic acid synthesis. So there you have it, oxidation, hydrolysis, and carbon chain extension. 3 core strategies that give you a complete playbook for building one of chemistry's most important molecules. These aren't just reactions on a page, they're powerful tools in a builder's kit. So now that you have the map and the tools, the only question left is, what will you build first?